Welcome to a short presentation and demonstration of ScanCAD International's products for legacy product reverse engineering, specifically looking at our automated PCB reverse engineering systems that are complemented by electrical test, that's flying probe testers, as well as CT scanning or CT X-ray for the non-destructive options. ScanCAD is a global leader for multi-purpose PCB reverse engineering inspection and measurement systems and has been so for the last 30 years, with over 1,000 customers installed in 50 countries. This is what we do. The agenda today will be focusing on the company overview, just a couple of slides. We'll talk about legacy reverse engineering, why this is something that is becoming a real big issue these days, and something that's getting bigger and bigger, as well as the technology specifically of the ScanCAD systems. We have several different systems to look at. Destructive process that is then complemented by a netlist and schematic generation capability. And then finally, we have some new non-destructive processes that are entering the scene today that could give you options if that is of interest to you. The goal of this session at the end is to understand whether ScanCAD systems really are the right thing to support your needs. Real quickly up front, we have over 1,000 customers installed in over 50 countries. We do go back over 30 years with our first systems being installed in the late 80s. This is what we do. That's the name, Scan and CAD. We scan and we make CAD data. Those original systems back in the 80s were primarily scanning films and hand-taped artwork and bringing that into a CAD environment, since most circuit boards were not designed in a CAD environment in that time period. Since then, we've been the missing link when CAD data has been lost or destroyed for any reason. We do have locations in the US and Europe, direct ScanCAD locations, as well as a global network of distributors and sales representatives in your area. We are completely based on flatbed scanner-based systems, so we're using a high-resolution graphic arts flatbed scanner, optical scanner that is used to image these circuit boards. Even in the non-destructive environment, we end up matching these flatbed scanner images with X-ray images and other data. Everything we're talking about today is PC-based, low-cost, easy to use. Our target has always been to have affordable systems. Our systems are sold into many industries, obviously defense, medical, aerospace, utilities, transportation, communications, etc., etc. All of these areas are having issues today with legacy electronics. We also have packaged our systems with companies such as Siemens, Philips, Panasonic, and some 9 other organizations where we package our product under their logo, where they integrate our equipment in with their capital systems. This slide here, don't be too worried about it. It's a little bit busy, but it really focuses on inputs and outputs. On the left-hand side, you can see our flatbed scanner is our primary input device, our optical scanner, but we do interface to flying probe testers, should you have those in your facilities. We have some customers that are interfacing our equipment to scanning electron microscopes. We have, again, a handful of customers integrating with the computed tomography systems, the CT scan systems, and X-ray systems as well. Though I should share with you, those systems are extremely expensive. Finally, obviously, as inputs, we have the actual board or stencils coming in, and in some cases these days, the film artwork and CAD data as well. But these days, we're seeing more and more customers coming from the actual physical circuit board where they need the data. They have lost all of their design data. They no longer have the artwork or the manufacturing data. So those are the inputs. On the output side, we actually give you several choices. You don't have to get everything. Some customers only want the PC fabrication data, which would be the Gerber 274X, the drill information, and of course images for documentation. Some customers would like to add more value and they need to get to netlist information, which could include the component footprints, and in those rich output formats of ODB++, IPC 2581, etc. Yet other customers would like to move forward and get the full bill of material data, centroid, part number, manufacturer data, component values, that kind of thing. In some cases, even moving that data to PCB assembly machines. And finally, some customers would like to go all the way from the bare board to a schematic. And not just a schematic in a PDF format, but in many cases up into a proprietary CAD system format. So this is a high-level graph, again, that just sort of gives you a snapshot of what we're going to be talking about today. Okay, that's it for the company overview. Let's dive into legacy product challenges. The reason you're probably watching this video right now is because you have a problem, and you're not alone. There is missing manufacturing data for many very important systems out there, such as air traffic control systems, transportation systems, communication systems, medical systems such as MRI, CT scan, those kinds of ultrasound type medical systems, legacy type systems that are still valuable, extremely expensive systems, but there are no spare parts. So data has been lost, corrupt, or maybe there's partial data. In some data, if there is films, they may have shrinkage or issues. Some customers have microfiche. Many times no schematics are available for repair. So this is very important. A lot of times the original supplier is out of business. Either they are completely gone, or they were merged, or that division was closed down and the products have been discontinued, yet you still have a major investment with these products. Finally, we have a term that's surfacing and becoming a bigger and bigger issue these days. That's DMS, MS, or DMS, and basically the diminishing inventories of spare parts out there. Products are simply being run well beyond their planned life cycle. I think aerospace is a classic industry where they design these products to run for 10, 20, 30 years, and yet they're running them for 40, 50, or 60 years. They still need spare parts. We need to keep these legacy systems running. That could be transportation systems like subway systems, train systems, the control switch equipment, telephone systems, etc., etc. So why reverse engineer a product versus simply redesign the product from scratch? Why would you even consider doing that? Well, the reason is most of these systems are just that. They are systems. There is one board that must interact with and handshake with many other boards in a system. And all of these have been certified and approved for noise, for signal integrity, etc., etc. In other words, we have working boards, and if you were to redesign a board from scratch, you would have to go through the certification process again, UL, CE, the FCC, FAA, etc., etc. You'd need to redo the environmental testing, your system testing. You're not going to want to stick that board into an aircraft and expect it to handshake properly with the other boards in that aircraft or in the air traffic control system. So, what do? You reverse engineer to precise form, fit, and function. Essentially, you are creating the digital twin. You are recreating that design data of that original part. It will then duplicate all of the original characteristics. Essentially, you are precisely and exactly duplicating that part. So we do use that term form, fit, and function. That's what ScanCAT systems are all about. That's what we're committed to, and that's what we've been doing for 30 years with those customers in 50 countries. So really, you have no need to recertify, system test, etc. And in some cases, yes, you may want to improve the design. You may need to miniaturize, modify, or do some sort of design improvement. Most of our customers are simply wanting to get the power plant back up and running, or get that system running again. In some cases, you may need or want to modify. And how better to start than with a complete set of functional board designs, schematics, net list, etc., and then work from there to move into a modified part. I think at this time, let's go ahead now and actually go into the software. It's more interesting to actually see the part and see what's happening. So let me open up this board right now, and we'll just take a look at it. This is ScanCAD's training board, so it's something, if you do get a system, this is something you will see. And I'll just give you an idea how the system works. We can zoom in, I can scroll up or down, I can move left or right with my mouse. You can also use the scroll bar on the screen here on the bottom or on the side of your screen if you want to move up and down with scroll bars that way. You can zoom in and out with your mouse, with hotkeys, etc. So it's a very easy to use system. It also has many layers. So for example, we can look at the second layer of the board. Here we've removed the solder mask, so you can see the second layer of the board. I can now move down through the board. Let's go to the next layer. We'll move that one, and we'll go I'm just moving down through the board to give you all the different layers of this board. And finally, the bottom of the board. We can toggle back to the top. You'll notice we have perfect layer-to-layer alignment. So I'll just go to the bottom and to the top. I'll zoom out. You'll notice the bottom. Okay. Basically, and you can see it's not read-write here. We're actually, we're looking at these layers as they have been put together from the top down, okay? From the top down. So this is a board that we have reversed engineered using a destructive method. That's why you see the inner layers are looking like the copper again. And we will teach you how to do that. And I have some slides on the processes we use for doing that. We also have in this sample job the same layers in CT scan, okay? So we actually have x-rays for the non-destructive process. So we'll be talking about that in this presentation as well. Okay, so these are x-ray layers. Here, x-ray layer of layer 3 there. And again, here is the copper layer 3, okay? We also, just for the matter of interest here, we are going to talk about counterfeit parts a little bit. I don't know if you guys can see this okay. I'll zoom in a little bit, maybe a little too close there. But this is an example of a counterfeit part. In other words, someone has gone in and intentionally done some damage to a layer that you can't see. So here is an image of the part in color. And so there's actually two different boards, right? Because this is actually the copper layer here, and yet that part, if I come down into it, into another board, you can actually see that someone has integrated a circuit in this board where it shouldn't be. So we're talking about how this system not only can be used for reverse engineering, but for counterfeit board and counterfeit component detection, okay? Because we are able to overlay CAD data at any point with these images and verify indeed what you see is what you get, okay? So let's just focus on this part for a second. Our focus now is reverse engineering. So I'll share with you what we do. Essentially, we will scan the board and you see the board in color. We will then color separate. We will color separate on the parts of the board that are of interest to us. In this case, we want to start with the pads, okay? So we color separate, and as you can see, we have the pads. When we want the legend, we will then color separate on the white text. But in this case, we're color separating on the pads, and the system will then create those pads automatically. So I'm doing something called vectorizing, which essentially converts that bitmap image into high quality CAD data, into flash pads, okay? So giving you that information here. So what I've done is I've just created those pads. They're put on a different layer. Let's go ahead and merge those into this layer. And CAD data appears as green. So in the end, we have green CAD data, okay? So that green CAD, we just made the pads for the top layer of the board. What I'm going to do now is we're going to go ahead and we'll just copy those using a copy function to get those pads into the second layer of the board. Okay, so we go to the second layer of the board and we have the pads copied in, okay? Now, on the second layer, we have some vias here that were not present on the top layer because they were under the solder mask, okay? The solder mask has now been removed. And so what we're going to do is we're going to vectorize again using a different vectorization function, And we will go ahead and capture those vias. And you can see that we captured the pads and the vias, most of them. Some of these we'll add manually. And we'll go ahead now and merge those guys into this. So we're actually building the Gerber data as we're talking together here. Now, in some cases, just so you know, the system is not 100% automatic. Some cases you will come in and you will need to come in and manually place a pad, for example, okay? So in this case, I'm going to go ahead and manually grab onto this pad, and we'll go ahead and manually place this pad, okay? There also may be a via here that is in some sort of a plane. So we can go ahead and place it here. I can also look at a different layer and make sure we're placing it properly. But just for the purposes of what we're doing here, I'll just go ahead and place this pad right here. Okay? All right, so we've created the pad data on the top layer. We've gone into the circuit layer now, created the pads we want. The next thing is we want to create our tracks. So we're asking it to automatically vectorize the tracks. So it will go ahead now and it will automatically connect the pads to the tracks and vectorize. Again, this is placed on a different layer. We call it layer 98 here. We can zoom in here to see if we like what it did. Seems like it did a great job. Okay, so I'm going to go ahead and merge this data in. And we now have pad data and track data. Now at the bottom of the screen, we have lots of things we can do down here. We can turn pads red, we can turn tracks red, and we can see here, for example, that the tracks are not going to the center of the pad. So we have a function in here where we automatically connect tracks to pads, okay? And bam, we then use a short track segment to maintain perfect electrical integrity of the circuit board. And again, we're matching perfect form, fit, and function, like we talked about. We are matching this board exactly. Now, this is a simple board, and I'm going to show you some more complex boards in a second. But I wanted you to get the concept down. We vectorize pads, both isolated pads like you saw on layer 1. We now vectorized pads that were connected on layer 2, and then we finally did the tracks. Well, now we have some plane areas, and this could be ground plane, power plane, or in this case, you can see this little tiny plane here. We'll go ahead and do a contour and fill, okay? So we'll go ahead and run that function. And we will now go ahead and merge that data in. And by the way, before I merge it in, let me just see where else it did that. It did that here. It also did some text over here. You see the text on the right-hand side? Okay, so it created the text, okay? So that's sort of the contour and fill function. We'll go ahead and merge that in. And you see we have wonderful Gerber data for this layer. It has perfect electrical integrity. So the tracks are connected to the vias and to the center of the vias, center of the pads, etc. And you would simply move through the board doing each layer as I've just done. You would then color separate on the legend on the first layer. I'll go back to layer 1 here so you can see that. And you would then do your logos, your silk screen, whatnot. You can do your non-plated through holes, any tooling holes, the border outline, etc. And you build a complete CAD package for this board. Okay, this is building the Gerber and drill, the PC fab data. Okay, we will then move to netlist in a second. So I hope that all made sense to you. I'm going to go ahead and quit, and I won't bother to save the work that I've done here, but I want to share with you a multi-layer board. And let's find this, there it is. A much more complex board. And I'll turn off the CAD data, and I want to give you just an idea of the kind of technology we're talking about here. So you can see here that we have what are called differential pairs. You see the timing is very important on this board. This board is a memory board for a laptop PC. This is a real live customer example. This is one of our customers that has permitted us to share this sample with you. So here's the top of this memory board. Let me share the bottom of this memory board with you. So there's an image at the bottom, and you can see how the letters have been reversed because we obviously have to keep all our layers lined up perfectly. And just like before, if I zoom in to any one of these vias right here, put my cursor on a via, oh, excuse me. If I put my cursor on a via right here, and I go ahead and toggle to the bottom of the board, for example, you will see that there is that via on the bottom of the board, okay? And by the way, the trace width on this board is very small. We have trace widths of 3 mil, 75 micron or smaller on this board, okay? So very, very high density board, and let's now go ahead and remove the solder mask. So that's what this looks like when you look at the copper layer, okay? Let's go ahead now and remove the copper. We're just now looking at the dielectric, okay? See the via right there? Let me toggle this layer 1 back on again. That's that via going through the board. See that? Right there. And you can see the plated through hole thickness, the barrel thickness, right, of that via, okay? Let's now go and remove the dielectric. We're in a ground or power plane here, and you can see that via was isolated on this plane here. Let's move to the next layer, and now we can see we're in a circuit layer deep inside the board. Again, differential pairs. You can see the signal integrity is very important. When we reverse engineer this board, it's going to match exactly the same trace width, the same trace length, the same thickness of copper in the plated through holes, the same dielectric thickness, the same copper thickness, etc., etc., etc. We are exactly form, fit, and function reverse engineering this board. Okay? There's a shadow. See the dark shadow in the background there? What is that? That is another circuit layer. And now the shadow from the layer we were just on is there. So if I go back in again, we can say we were on that layer 8 of this board, and now we're on layer 28 of this board, where we've looked at these two signal layers deep inside the board. And if I start coming out the other side, we can go to a ground or power plane again, etc., etc. And finally, you work your way right back out to the bottom of the board. So we can move all the way through the board. Okay, so that is looking at the ScanCAD system, and now we can go back to the PowerPoint. So I just wanted to give you an idea of the process that we're using. So yes, we can use a mixture of populated boards, bare boards, x-rays. They all can be mixed together along with stencil images, as well as if you have existing Gerber or CAD data, import that as well. It's possible you have a Rev 2 board and Rev 1 data. So you'll have a leg up on that. We can overlay the Rev 1 data and then modify to match the Rev 2 board. Okay? Let's now step through the technology itself. This is the platform for the system. It is an adjustable bench, meaning it can be, you can sit down or stand up. These are adjustable legs. You provide your own PC. We provide everything else that you see here. As a matter of fact, the desk is optional. You don't have to have the desk if you don't want it, okay? Some customers prefer to put the system on their bench, but essentially the scanner, the flatbed scanner, sits in a tray underneath, and it is calibrated with a NIST certified glass calibration plate. NIST meaning National Institute of Standards certified glass plate, so it supports your ISO certification. So it is calibrated, it is highly accurate. The glass plate sits on a shelf under here, or if you use your own bench, you'll want to protect it in that way. Essentially, the scanner faces up, your parts face down. We are able to image parts with components on them, or if you have some parts that you have wet glue, epoxy, solder paste, that kind of thing, because you can also use this system for inspection if you want, you can image those here as well. The lighting can be top or bottom. The standard system has reflective lighting only. That's from the scanner. If you get the optional bench with a top lighting here, then you would have a top light or what's called transmissive lighting. So transmissive or reflective lighting. The standard system with the scanner only would have just reflective lighting. If you end up with the optional bench desk here, you can then have the top lighting as well. I'm going to show you a video now, so please watch this video of us placing a part on the scanner and performing the scanning process. So you can see that it's a simple process to simply mount a board on the system and scan it. As mentioned, when you move through that process, you do end up with a perfect form, fit, and function. I just took you through the two board examples showing that. And we are able to eliminate some of the errors that you actually will see in the board. There is something called drill runout. You could have possible solder mask and legend alignment errors, that kind of thing. When we recreate the data, you're able to recreate in such a way that you match the precise form, fit, and function, but you are not going to also integrate manufacturing defects that board possibly has on it. And believe me, you'll be surprised when you look at your boards just how many defects there are on these boards. It's sort of shocking sometimes. But in the end, you are having a board that is recreating the original manufacturing data. Because remember, many of these legacy boards were hand digitized, they were hand taped. There's a camera step and repeat process and a reduction process. So many of the boards that you're going to reverse engineer are they may be sort of shocking to you as you move through that. Finally, when you do go through the process of reverse engineering, you do have access to lots of design rule check features, such as checking air gap for air gap violations, layer-to-layer alignment issues, feature registration, etc. The whole idea here is to recreate data that will match the original design data for the board and remove any of the specific board level defects that might be there because of the board that you're reverse engineering. We are creating what we call the digital twin. Okay, the Gerber data that comes out, what are we creating, is 274X, obviously used for the stencils, pad masters, solder masks, 6 screens, all the photo plots, and your test point data. In fact, on the right, you can see just a sample image of that 274X data. We obviously are creating the drill programs, both for your plated through hole and your non-plated through hole areas, and your route programs, as well as documentation. We are giving you full color documentation, calibrated, high resolution images of every layer so that you have a fully documented process. Now you may ask, how is it that you delaminate the boards? How do we get such nice, beautiful images of those interior layers, those inner layers? And using our destructive process, you actually destroy the board. And for those customers that are working on boards that do have very fine features of perhaps below 5 mil traces and spaces, you might want to consider our optional precision material removal system, PMRS. This system will delaminate the PCB. It's in a very controlled environment, in an office environment. It's very safe to use. So you are working obviously with copper and lead and other materials, and we will teach you how to work with this in this HEPA filter type of a system. So it is a destructive process to get to those inner layers, and we can step through that. Here's some images of what we use that PMRS system for, Precision Material Removal System. It obviously will remove the solder mask in a beautiful way. It can be used to remove dielectric, and here we're showing you zoomed in images of this. And yes, the system even has an optional conformal coating removal option. And why it's optional? Because it includes the ESD capability to prevent damage to your components when you're removing the conformal coatings. So all of that is all part of the PMRS system for you. And I'd like to show you now a short video of the PMRS system in operation. Okay, moving on now to our next technology product for you to look at would be our bill of material creation, the ability to scan populated boards and generate the bill of material that's needed for you to generate net list information, and certainly needed to generate the schematic information and move data up into your CAD environment. So we are able to scan a populated board or a bare board and create the component centroid, rotation, reference designator, package ID, and permit you to put in the part number. Some customers put in the value of the components as well. This is a great time to go ahead and go back into the software and just show you some images of populated boards, so you can see what they look like on the ScanCAD system. So we'll go ahead and pull up this image first. And I'll zoom in a bit so you can see that. And what I'll do is I'm going to go ahead and turn on the assembly data or the bill of material information. We'll go ahead and display that. Instead of a gray box, we'll display that with a window. And so essentially, if I toggle this on and off, you can see that we have data here for the board that's been created on the ScanCAD system. And if I'm to, for example, if I snap to this device, we can see at the bottom of the screen here that this is U2. It has, the reference station here is U2. It has a rotation of 90 degrees, has a package ID. It's a Motorola part number such and such. And in this case, the customer actually wanted to have this on a Yamaha machine as far as doing its placement. Well, it's certainly much more interesting to have a color image of the board so you can zoom in closer and see that Motorola component. If I now single step, you can actually go through the board and it will jump to different components, just dumping through the board, and at whatever zoom level you want. You can get in very close or you can zoom all the way out. And basically the system has all the data in the system, not only created from the board image, but it's also in a table format. So we can actually look at the parts here in this table format that can then be output as your bill of materials. Okay, so here's some Motorola parts, some Intel parts, Kyocera, etc. Okay, so essentially, I'm just giving you an example of a board here. Let me go ahead and let's bring up another example. Here's a mixed technology board. So this has both through-hole and surface mount devices on it. Again, if I turn off the color image, you can see the parts listed, and you can look here. This has an example of jumper settings also. So some of your boards may have jumper settings, etc. Oh, by the way, I should mention this for legacy parts. You're going to see a number of jumper wires on your parts, and that's not a problem. You're going to want to include those as yet another layer for the jumper wires and then some jumpers and stuff that they put on boards. Because again, for form, fit, and function, in many cases, you have to exactly duplicate the board as it is. You will not want to change design. So if you need to add a jumper wire someplace, then add the jumper wire so that the spare part will go back into that system, in that aircraft, or into the air traffic control system and function exactly as the system that was there before. Okay, again, this is showing you a popular board and the ability of the system to scan in a focus kind of mode because it has that capability. Going back to the PowerPoint presentation, let's now talk about the net list and schematic generation. So essentially what happens is that Gerber data and that bill of material data that's been created in ScanCAD's products called ScanFab and ScanPlace are then brought into the netlist software module, which we call Convert Plus ARE. So essentially we have this ability to recreate the Gerber and the drill data with ScanFab. ScanPlace permits us to build the bill of material and the Centroid data, which then flows into Convert Plus. In Convert Plus, we then create the package footprints and we do the pin numbering. At this point, we are then able to output the various netlist formats that you may be interested in. The IPCD 356A format, which is a great bareboard test kind of format, as well as the more feature-rich component-loaded formats of IPC 2581 and ODB++. We are able, by the way, within the Convert Plus product, able to compare netlists from the flying probe, netlists that were generated from the ScanFab, ScanPlace process, as well as netlists that are created using the flying probe tester. We'll talk more about that in a minute. Here's some examples of the IPC format, example of the ODB+ format, and then now let's talk about schematic generation. Once all of this is done, we take the data that we just created from the netlist and all of that, we then merge that into our schematic generation module, and we're actually able to now make schematics. Schematics can be output in PDF formats, or schematics can be uploaded into a variety of CAD systems, as you see on the screen. So essentially, we can start with a populated board and end up with a schematic and have all of the manufacturing data that you need to actually recreate that board. Here's some example images of schematics. And you note the pin numbering is all the pin numbering that you would expect. The images here. Okay, everything we talked about to this point, all of the products have been focused on our traditional destructive type PCB reverse engineering products. Okay, these have been complemented in the last couple of years with some non-destructive capabilities within the ScanCAD family of products, specifically ScanFab ND for non-destructive. So we would have the ScanFab ND with our Place product, our Convert Plus, and the scan generation module. What the ND product is adding is the ability to import images from CT scan, X-ray, and scanning electron microscopes. We can then import these images. We can scale the images to match the calibrated optical images of the top and the bottom of the board or the components. Extremely important because in many cases, the CT scan, X-ray, or SEM images are not dimensionally correct. Obviously, that does you no good if you want to create a new board to form, fit, and function. So we have capabilities within the ND product that will scale the images properly and then be able to process those grayscale images into monochrome images that are then able to use those same automated functions I showed you a minute ago for pad vectorization, track vectorization, and contour and fill. And yes, of course, for large images, we have the stitch capability to be able to handle images larger than or boards larger than the A3 of the system. Again, our system can process huge images. I mean, literally, I think the largest image that I've seen is literally 5 meters long. So not in the electronics industry. This system is used outside of electronics as well. By the way, the ND system has this independent netlist verification and creation capability, so it does support a whole variety of flying probe testers that are out there. The sources of data are the same in the ND system, starting with the bare board, a populated board, old Gerber data, etc., film paper. But now we add the ability to bring in these X-ray or CT scan images. This is particularly helpful in the ceramic or alumina area or LTCC type devices. Okay, and again, component level. I'm going to show you a component here in a few minutes so you can see this. There's a variety of scenarios involved. I encourage you to get the PowerPoint presentation because I have to go through these very fast for the video, but just want to share with you that if you have one PCB, there's only one board left in the world, then this non-destructive process is something that you might want to consider. Essentially, you'll use the ScanCAD optical tools to image the bottom and the top of the circuit board, populated or bare, and you will use the X-ray to image the inner layers. As mentioned, we will then scale the CT scan images in the ScanFab ND product to match the top and bottom layers of the board so they optically line up, just like I showed you a second ago with the product I showed you, the training board. And the board is not destroyed in this process. So you're able to actually create a net list from this reverse engineering data. Now, the advantages of using this is that it does work with one PCB. You can get independent net list validation because of our integration to flying probe testers. You are, in theory, getting correct form, fit, and function. And I say in theory because the X-ray images must be high quality to do that. And there are artifacts that are a big problem with X-rays these days. So you should not assume that that's the case, but we are seeing this improve literally every year, significant improvements. So this is a non-destructive reverse engineering process. What are the disadvantages? It's extremely expensive. These CT scan machines are not cheap. They are very difficult to get high quality images. They take a long time to get those images. I've been told up to 18 to 20 hours in many cases, even for a small to medium-sized board to get a set of images. The form, fit, and function may be error-prone because of blind spots from the scan, the X-ray images. Really, the proven process today is the destructive process, assuming you have more than one board and you're confident and comfortable destroying that board. Another worry factor would be the IC devices. If you are scanning the board populated, we have been warned, for example, by NASA that they do not permit any of their ICs to be ever X-rayed because they are damaged, and there are some studies that talk about that. So you need to be careful with your IC devices, your active devices, if you are going to run them through a CT scan system. The next scenario is one where you are able to destroy one board. You can get two boards, so we destroy one. We completely reverse engineer it, get the net list, all the manufacturing data, use the second board to go ahead and validate the data from the first. So this is an independent data validation using a flying prober. Very smart process. This is the preferred method. It's very fast. It's least effort. It's the lowest cost. It's safe, accurate, gives you that independent net list validation. And it's just super. If you don't have a flying probe, no problem. You can send it to many companies, or contact ScanCAD, and we can help you, put you in touch with a company that will test the board for you. So what's the negative? It requires two boards if you want validation. One board is destroyed. Do all of our customers validate? Absolutely not. I would say only 5% of our customers that use our CAD systems today for reverse engineering actually validate the boards, because the fact is the system does such a phenomenal job of reverse engineering that they really don't need to validate the boards. But if you want that extra level of satisfaction, then do that. Now, there are scenarios where you only have one board and you can use a flying probe tester. The ScanFab product helps you through that process, the ND product. Essentially what we do is we scan the top and the bottom of the board. We then create all the data needed to run a flying probe tester. You then run your flying probe tester using that data from the top and the bottom of the board to create a net list. So you're essentially using the flying probe test to create a net list. And then we destroy the board. We create the Gerber, the drill, add all the component information, create a new net list that you then compare with the first net list to verify everything's okay. So the advantage is here that it does work with one PCB. It is safe, accurate, fully independent validation. It does support correct form, fit, and function. It doesn't have the problems with X-ray artifacts, and it can be a real lifesaver if this is the last board in the world situation. The disadvantage is it does take longer processing time because you're going to be running this on a flying probe tester. Obviously, the board is destroyed, more efforts involved, but if it's the last board in the world, you don't have a second board, this is the recommended procedure. If form, fit, and function is not required, we have a situation here, a scenario where the board's not destroyed. We run it through the flying probe test. You get a net list, and then you use a second board to validate that net list, and you can move forward. This is particularly helpful for those customers that are really focused on repair. If they just need a net list and schematic for repair, but they are not trying to build a board. In other words, form, fit, and function is not required. Okay? Big warning. Flying probe testers, are they 100% for reverse engineering? Are they 100% good? And the answer is maybe not, especially since some of these legacy boards have issues and whatnot, and they might be damaged in some way. Flying probe testers will not give you reliable net list data if there's an internal broken plated through hole barrel or damaged pads or some other kind of board level problem. Okay, so if you bank your company on this, that still could be a problem. We strongly recommend a destructive process on one of the boards to get you solid data. Okay, here's another scenario running flying probe. Again, one PC, this is only, if you're for a repair facility, that kind of thing. All right, as mentioned, we can use this system to detect counterfeit boards and components. So how do we do that? I'd like to go ahead and share an image with you. So let's go back into the software. Let's quit, and we'll see if we can find that, that image in here. All right. So here we have a component, and let me go ahead and zoom in a little bit. So basically, this is a CT scan of a component, and we can actually see the wires coming down to the pad sites on the die, okay? And again, this can be used for reverse engineering if you want. We'll go ahead now and just move our way down into this board. Let's go down and move to another layer here. So again, the top layer, and then we come down, and we are able to generate CAD data. Okay, so I'm showing you the vias right here as you move down through that board. So what am I sharing with you here? We can reverse engineer this, this component and the substrate below the die, okay, this BGA. Let me go ahead and let's keep going down into this device some more. So here we go. I'm turning off the CAD data here, so you can see there's the image, there's the CAD data that's been generated, okay? And we'll just keep going down through the board. So this board, this is a real live example of a board that's been reverse engineered. And again, it has several different drill files. So it has blind and buried vias. So there's actually 3 sets of vias on this job. And then finally coming out, we can see color image here of the bottom of the board. So this again was, as I mentioned earlier, you have an optical image from the ScanCat system that you then scale the X-ray images to match. And obviously, if you're going to check for a counterfeit part, we can look at the die, we can look at the wire bonds, and we can compare all of that back to CAD data to verify this is indeed the part that you were looking at. Or, well, in fact, let me just quit out of here for a second and let's take a look. I'll just look at the surface of that part. There we go. So again, looking, here's a color image with the balls still on the part. So you can see, again, this is what it looks like before you start removing and going through this destructive process to look at this component, or the X-ray process to verify everything's okay. So I just thought I'd give you an image of a colored part there. Let's now go back to that example I showed you at the very beginning using our training board here. And you may remember that we created the data, for the Gerber data on top. We went through that process of building all the Gerber data. Well, remember that we also can overlay CAD data in here. So for example, what I can do is let's go ahead and bring in that layer 2. So here's the layer 2 information, and here is the CAD data on layer 2. You see on the screen, okay? And let me turn off the assembly data here, because we don't need the bill of material right now. So that had the bill of material data. And we have the color image of the board. And we, again, as you remember how the system works, you scan in color separate to the blue, make the CAD data, etc. Well, the same is true if you were going to be looking at an X-ray. So here we have X-ray. And now you can see there's something very strange going on, right? So we have a situation where someone has altered the data on this inner layer, and they've actually gone in and put in some secret or spy circuitry. So this does not match. This is what the board's supposed to look like, and this is what the board actually looks like. So this is an example of a counterfeit board, or someone putting in something that shouldn't be there. Now, most customers are actually checking internally to see if the track width is the right size, if the barrel thickness is okay, if there isn't any drill run out or some via violations, manufacturing defects. But in this case, this is a real live example of a counterfeit part detection. So that's why we bring this up in the end, is this is another side benefit of this system. Not only does it do a great job of reverse engineering, but it does that. All right, let me finish this presentation by just saying thank you. Thank you very much. We hope you will join us with one of our reverse engineering systems if this is something that will meet your needs. We're more than happy to have you talk with one of our local representatives or distributors and talk to you about your parts, your application, your situation, to see if we can match our equipment to help support your needs. Hope to add you to our 1,000+ customers in 50+ countries and to support you for the next 30 years as well. So again, ScanCat systems are proven, they're economical, easy to use. These are offline, obviously. This is an offline system. These are accurate, calibrated device supporting your ISO certification. Many inputs, many outputs, fully traceable for your compliance programs. So in other words, when you're creating form, fit, and function, you're creating something that meets or exceeds your criteria. your compliance criteria. Multi-purpose, yes, the system not only reverse engineers, but we have optional modules that will perform inspection and measurement as well. Feature sizes down to 1 mil. We have Japanese customers that are actually running this system down to 12 micron, literally a half mil right now, half mil features in Japan in clean room environments, okay? Upgradable, we've had annual releases for this software for the last 30 years, and the data that was created on our systems 30 years ago can still be run on our systems today. We maintain forward compatibility all the time. We protect your investment in ScanCAD systems. So what are we focused on? Form, fit, and function. We're focused on that digital twin. We look forward to supporting you in the near future. Thank you for your time in this presentation. Please let us know how we can support you.